sort of copy conflict and merging.
Yeah, and then there's a different one that's very similar that it's called lock.
Yes.
And then you change something and you unlock, right? And it says that the locking one is much safer and it's much more readily used, but then you're teaching us the copy and merge.
Yeah. Yeah.
And
Yeah.
I'm just wondering what the major difference is. Like they're very, very similar, but
Yeah. So
when would you use one?
right. Yeah, it's somewhat of a generational issue, actually. The so so if you look back a couple decades, both these issues have to do with gating or managing edits that two or more different people want to apply to the same file that's shared. Okay. Gosh, it's terrible English. But so maybe here we have a set of files associated with a project, right? And we have a set of people associated with this project, and these different people are working on these sets of files, and two people may be interested in working on the same underlying file, right? They each have a need to access that file. Now, in lecture, and indeed on the lab that you folks will be doing this week, we talked about a strategy for managing that access using subversion. People updating periodically. They can modify the files that they've updated very freely. And when they check in a file, it will let them know if it's clear sailing, there's no structural conflict detected with an existing file, or if there's some conflict which requires their resolution. Okay, and we saw basically how that can lead to, Harry and Sally jointly at the same time actually editing some file, call it file.c. I know you thought it'd be foo.c. Well, I'm a little bit non-deterministic. So file.c, both ending it at a time. Maybe Sally checks hers back in first, right? And Harry's working off his changes off the old version of this. He tries to check his in, and there's a conflict. And you folks will be rehearsing this, not 24 hours from now, for some of you, using the lab for this week, where I have you go step by step by step through that process and how it plays out. Okay. Ultimately, it was up to Harry to kind of go fix up his version, right, so that he could kind of make his changes consistent with Sally's and then check it in. And remember, there was a whole series of processes along there. So there was an SVN update, for example, and an SVN resolve that had to take place, and an SVN commit. So here, in this process, we actually had 4 versions of this file created. One that shows sort of his and Sally's changes kind of side by side, so he can choose which of them he wants to include. Another one which showed his code before he went to check in. Another, it's the version of the file before either of them modified it. And finally, a version of the file with just Sally's code, as I recall that 4th one. I'm going to have to think for a bit. But in any case, there were 4 versions of the file created for this conflict, and he had to go through and sort of figure out, okay, what does he want to do to make his changes consistent with Sally's, do an SVN resolve, SVN commit, check that all the time. Okay, So, and that's the most common way with subverting the hands of things.
That's the common modified merge.
Yeah, yeah, definitely. Yeah. So another approach is based on locking, and this approach actually goes back further. It was quite dominant, 20 or so years ago, 20, 25 years ago. And it again had to do with the same situation about gating access to some underlying files. But it was it was more rigid, it was less flexible. And what happened there is that when Harry or Sally wanted to access this file, one of them would take out a lock on it, okay? And what I mean by that is that, say Sally was the first one to go reach that file. She would say, I want to modify file.c. So I'll do a checkout on that file, okay? She'll do checkout file.c. And that's all one word. And this was supported by CPS, for example, the code versioning system. So she'd do this checkout, and this checkout would go and actually get the latest version of this file onto her machine, but it would, moreover, mark it on her machine as something that could be modified. On others' machines, they couldn't modify it by default. It was in a locked state. It was a read-only file. And it was by virtue of doing the checkout on it, it became read-write for her. Okay? So she would do this checkout, it would become read-write. She could then go and modify it, and she could, when she's done, check it. Okay? So she can, when she's all finished, she could do a check-in with file.c, and it would put the contents of her file up on the server, and her file on her disk would then be marked as read-only, because she's done with it, right? And that would allow Harry to go modify it. Now, this system really discouraged, if possible, simultaneous edits. So she would do this checkout, and maybe that would be at 10 o'clock in the morning. Harry comes along at 11 o'clock. He wants to modify this file, but he sees this checked out to Sally. And so by default, he would wait. He would wait until she checked it back in. So I don't know if you folks have worked collaboratively on documents, but it's very common these days for people who are not computer scientists to be exchanging, say, a Word document, and one of them will say, I want to take the lock on it. And actually, I think that terminology derives from exactly this sort of system. They'll say, I'll take a lock on this file, I'll work on it from now until 2 p.m., and then I'll circulate it again via email. And during that time, no one else should be working on it, is the idea. Why shouldn't they be working on it? Well, because if they work on the same time, then you're going to have two modified versions, and neither builds on the other directly, and someone's going to have to go through the work of making them consistent. So that was sort of the general rule, that you would let someone else check it out, and you would wait until they had checked it back in before you checked it out. Okay? So they kind of used this locking protocol. Now, sometimes people would override that. Sometimes people would say, look, that's all well and good. I'd love it if Sally finished her edits, but I can't afford to not modify it now. I need to modify mine now, and torpedoes be damned. I'm going to come back to this once Sally's checked hers in, and I'll go through and merge the two. And I'll do it with less assistance than you have now. So the tools weren't as advanced. And so they would go and override the system, override the lock, modify it on their own machine, and when Sally checked hers in, they would get that version and they would manually merge the two. Right? So they would do a merge on the two of them. So this involved a thing called locking. Okay. It was a locking protocol, and by default, it was locked after you did it was locked for other people. Well, in general, and it's only once you did a checkout that you had the lock. You one who could modify it. And really, for the most part, you were viewed as being the designated one, the only one who could modify it during those periods. Again, people did work around it sometimes, but this locking prevented, two people from modifying this at the same time. These days, that's not regarded as quite as acceptable, and people have better tools to merge in their changes to this file. One thing I didn't emphasize that's different these days than it was back then is that the tools are better at merging automatically portions. If you've modified different areas of this file, maybe, for example, Sally has modified the function foo and Harry has modified bar, and they're in different areas of the file, it will just merge them. It won't actually report a conflict per se. It won't say, Harry, you can't check your file in until you merge it. If they both modified foo, if Harry, to make this consistent, this is Sally, maybe she modified foo. If Harry modified bar, no problem. He goes and he does an SVN commit, and it will just commit his changes. It'll say, oh, Sally modified foo, and this guy modified bar, no problem. I don't see a conflict. We'll check it in like that. And it's only if he modified foo, if he modified some overlapping lines, that you get this conflict where he has to resolve it and so on. By contrast, back in this era, with the checkout and check-in sort of gating, it was things were done more cautiously along those lines, and you would do manual merges often, double check everything, and you do have to be careful about this. It's true. Maybe Sally modified foo, maybe Harry modified bar, but maybe there's some dependency between them that isn't caught, and maybe his modification to bar had called foo with a certain number of parameters, and Sally added another parameter as being required by this, and his changes now break. That is possible, but this is it's a little bit more of a rigid protocol with locking. Yes? It's true. So if you have good contracts in place, it'll lessen the chance of it. The issue is that there is a risk that Sally will modify the contract here, so that she'll actually change the contract, which would leave Harry in difficult circumstances if he's operating off the old contract. So what you should realize is Subversion merges a lot of changes from two different people on the same common source. One person checks it out, one person does an update and starts modifying it. So this is Harry, this is Sally, they're modifying it in parallel, they check it in, and it says, fine, no problem, because they modified different areas of the file. You will see that tomorrow, many of you, with the lab. Okay, you'll see exactly how it merges those, and you'll see a case where it can't merge them because you modified the same line. In this case, a make file, and it says, I don't know what to do. Go off and fix it. But it's this sort of situation that's the worry. And Subversion, in contrast to these older systems, CBS automatically handles a lot of those merges to allow, greater productivity by people working in parallel. At least that's the idea. So that was a good question. Other questions? So I could make this is about reviewing, review various topics that we've covered. I could flip through slides that we have gone over, or I could, I could go present slides that I brought here. How are people feeling about points? Great. Okay, that's good. We're not jabbing you, yeah?
I was, I thought I lost my vinyl where we realized it was changing the instead of actually file.
Oh, okay,
I was seeing Dash that's what it's like when you lost my vinyl.
oh,
Because I was going to the debugger and sort of all my games that was
right. Yeah, so, certainly with make, you gotta know what you're dealing with. I was referring here more to sort of the whole issue of, pointer arithmetic and stuff like that. I mean, do people want a discussion of that? Is that
It sounds like a very bad idea. Why would you do it?
pointer arithmetic? You just gotta be very careful with what you're doing. Yeah.
Kind of related, just a general question about pointers. Are they still really common in modern software engineering development?
For C, they are the name of the game.
Yeah. What about C++?
C++ you still use.
Isn't that what Java is like?
Yeah, I was gonna say.
Java references they function like pointers. There's a huge difference in the sense that number one, you don't do pointer arithmetic on them. Number two, you don't have the option of doing loosey-goosey stuff with that will lead to whacked out situations like where you're pointing off into Never Never Land. And third thing is you don't have to allocate and deallocate manually. It takes care of all that for you. And those three things combined to mean a lot less, just unbelievably less headache. Unbelievably less headache. Believe me, so the deal with, the danger with pointers, of course, is, okay, so you have this nice array of, ints, right? This is an int array of however many it is, eight things, right? And you have a pointer to it, to the beginning of it, right? You could just refer to this, so I'm gonna make this here I could refer to this as A, and that would be that first element. Alternatively, I could refer to it. Can anyone give me another way to write this first element?
0.
Yeah, so it's ampersand A of 0. Okay. What does this ampersand mean? Address of, yeah, it's the address of this, where this value lives, which is here, okay? And if I have a pointer to that, I could say, some pointer, int star p, right? I could say p equals n, or alternatively, I could have said p equals this thing. It's the same value. And then I could say p plus plus, right? And if this is, okay, if these are, how much do I really want to go into this? We're going to start, for simplicity, with characters here, and I will graduate you to integers in a moment. So these are character pointers, like a string, right? These are strings in C. So we could have this character array, and we kind of here, and if I say p plus plus, it goes from pointing to that character, and pointing to this next character, pointing to this next character. P will point successively here. And the danger is, of course, that what will happen? Yeah, then it's pointing off into this space. And bad things can happen when it points off here, because it may point to a place where it's like the end of the world. and it goes here, and the operating system says, segmentation fault. In other words, you've pointed beyond the end of the known world. You've pointed to illegal places. You're snooping around. You're out of here. And it evicts it from memory. It says, like, game over. You're gone. Just get out of here. And it will shut down that person. Right? That's one bad thing that can happen. Another bad thing that could happen is you're right to it. Now that becomes really nasty. You're going, and who knows what you're writing to here. You could be writing to the value of pi or something like that. And suddenly you change the value of pi to be,
6.
Yeah, to me, that's right. 6, or to be even worse, to be -2 or something like that. And you change pi by your lose a pointer, because it's pointing off here. Or, even if you don't do that, folks, you may deallocate P. So someone says, you know, they want to free up some amount of memory, and now, or in this case, this is where I really want to. Yes, look, you folks may be C programmers, so I've got to save you. In the sense that I need to straighten out some things in your mind. So this thing is not something we're going to allocate explicitly. I mean, if we have a char A of 8 and C, if that's, you know, how this is declared, it's going to actually point to some fixed amount of memory associated with that, and maybe the function that has this memory associated with it returns, and then P is pointing off into Never Never Land again. It's pointing off into some space that used to have A, but now is just pointing out there. It's like, you know, it's like you're referring to the barn, and the barn burns down, and the barn's gone, but you're still telling people, like, meet me at the barn. And come and look, and there's no barn there anymore. Believe me, some of my veterans have been through that. They say, you know, well, you turn where the barn burned down 10 years ago, or something else. Okay, well, I don't know where to go. So the point is that pointers can become no longer valid because memory changes. So if I have a function foo, and it has in it this int of A, you know, some array to be of length 8, and then I could point some pointer P, int star P, to be point to the first element of A. Great. And then I can refer to P here, and I can, you know, assign to it, and all those good things. But when this, I could return P, right? I could return P as the value of this thing. And you know, I could return P, but it doesn't make any sense. It's pointing off into something here, which is now gone. It's gone because we had, you know, maybe foo was called by bar, and that's an inversion, eh? So bar called foo, and so here we have bar's activation record, we have bar stack frame, and we have foo stack frame on top of that. And this array, you know, had 8 elements up here, right? And P pointed to that just great. Here it is, pointing to that, and maybe we did a P++, and whatever P points to, went to that one, right? After that, and so on. That's great. But then we return the value of P when we return from foo. So we return, you know, a pointer to this thing which no longer exists. That's bad. Because now it could point to something else, and someone could probe it. Someone could modify what's there, and you have no idea what you're modifying. Welcome to C. And it's dangerous. You got to know what you're doing. And so this is some of the dangers with pointers. But let's talk about going from characters, where each of these might be a byte traditionally, to going to, although with internationalization that's changed, to going to an int. Now, each of these things, if we have an int star P, now we may be pointing at the level of bytes, say to 2 bytes in a row, right? So this is the first byte here in the array, maybe? First int in the array, it's 2 bytes. This is the second int, it's 2 bytes. And the third int, it's 2 bytes. So if we have a pointer P that points here, and we increment it, it's going to increment to point to this next integer, okay, which is 2 bytes later, and then maybe we increment it again, and it increments and points to this next one, right? Does that make sense in terms of the bytes? There's a sequence of bytes. That's how actually the ints are stored. And it can go and sort of chunk along to the next one, and next one, and next one. And this is an integer pointer P. What makes C particularly dangerous is you could turn an integer pointer to a character pointer by casting it. Pretend like this number is now, it's dangerous to because, well, it affords you certain abilities which can be, by which you can accidentally hurt yourself badly. So you could say, okay, now treat this pointer as if it's pointing to characters, and now let me increment it one by one on those. So that's kind of dangerous. In any case, pointers can be incremented, decremented. You can add things to them. So you could say, for example, p, plus equals, 5, and it would, if this is an int star, it would go from this first int to the second int to the third int. It would go 5 in and use that as the location. Well, for an int array, you can't.
You can't.
You can force it. You want to see?
So what happens?
You want to see where I can force it? Sure. If you really want to see that, okay. Yeah, I can force it. It's horrible. Okay, fine. You want to see how I can force it? Okay, you want me to point to this? Isn't it? Okay. First of all, in some architectures, it won't be supported. So you may cause a bus error. Okay, you may cause the processor to say, "Can't do that. Can't do it." But you can, in general, treat these things this. What you do is, okay, fine. So I have this integer pointer, and I call it p. It's an int star. Okay, fine. First, I cast it to a char star. Okay. I say, basically, treat that as if it's a character pointer. Now add 1 to it. Okay. And now cast it back to an integer pointer. Done. Now, as I say though, some architectures say you can only have an integer pointer that points to even things, and it will actually cause problems if you try to write to this. But C does allow you to assign this. So, do people understand what this means? I mean, I don't want to get into Arcana and scare everyone off. This is not Halloween. So look, this is an integer pointer. It's pointing to something here. And now we say, hey, C, look, I know what I'm doing, okay? I know what I'm doing. Let me treat this as if it's a character pointer. And it says, fine, gloves are off. This is a language with unions in it. You could treat this sometimes as an integer, sometimes as a character. As far as C is concerned, that's fine. Up to your business, buddy. You got to watch out for yourself. So you want to treat this as a character pointer? Be my guest. Fine. Treat it as a character pointer. Okay, so now we have this number. It's pointing to that same location. But we can treat it as if it stored characters. Great. Well, I'll add 1 to it, right? That's just the next character in line. Great. I'll add 1 to it. As far as C is concerned, hunky-dory. Okay? We're pointing to this next thing. Okay? And then I could say, okay, now take that thing and pretend as if it's an integer pointer. Fine. Take it back there. And now we've got a situation which we couldn't have gotten if we had just treated it as an integer pointer, which is we're pointing to this thing which is halfway through the integer. That's bad news.
So now what you could do is what makes the first
Yeah.
the first 4 bits and the last 4 bits.
Yes, and if you don't think this happens, sometimes it happens. It's horrible. And you don't want to do it. You want to stay away from that as if it's the plague. Because you can get yourself terribly confused, but yes, you can do it. Ladies and gentlemen, this is the power, the allure, and the danger, and the hideousness of C all wrapped up into one.
That's actually kind of conventional when talking to Armlock. It sounds really wrong.
Well, yeah, it's a dangerous thing because once you start, doing this, it's deuces wild. I mean, you can really easily get yourself bugs that are almost impossible to figure out.
Yeah.
It assumes you know what you're doing. And the problem is that when it's 11 o'clock at night and you're working on a late assignment or you're working on the thing for the client, sometimes you don't know it. You're confused. You make mistakes in your reasoning, and you end up doing something that's really silly, and it takes you 3 days to find it at that time the client is fueled.
Or you give it to the class, it destroys everything they ever loved.
Yeah. I mean, it used to be much worse because, ladies and gentlemen, and still on some operating systems, it doesn't enforce the end of the world, so you can start to write into some other thing that's going on in the same computer. So my code can start writing your code over your code and start destroying the operating system, and start writing to things in the operating system and getting it all confused about what files are open and so on. And bad things happen. What's that?
Which systems will have that behavior?
Well, certain embedded operating systems. But the system that was most famous for allowing that in your lifetime was DOS. So MS-DOS, but you could actually do that in Apple too. Did you ever hear about that thing that used to happen with Apple Macintoshes? Where there was you know what their icon was for an error that occurred? It was a bomb. It would show this bomb. And there were recorded cases, and I kid you not about this. This is actually true. There were recorded cases of people calling up Apple who had fled their houses because they thought their computer was going to explode. And they said that, a bomb appeared on the screen. And it had a lit fuse and everything. And believe me, I saw it. And ladies and gentlemen, I may have seen it because of this. This sort of thing. Seriously, you can, with Apple, with Macintosh operating system, just like DOS, you could have pointers that get loose. You start incrementing them. You think you're in same territory, but you're actually pointing off into Neverland. What you're doing is like you're scanning for a 0 byte at the end of a string, and you're not encountering any 0 bytes. Oh, there's still none. Oh, I found a 0 byte. And it turns out that points into the operating system's storage for, again, what files are currently open, or what data has been read from a certain file, or what data should be written to a certain file, and you start modifying that place. You start appending characters to what you think is the end of a string, but is actually the end of the allocation table or something like that. And it writes, and it's all off here, and then at some point the operating system says, my file allocation table is corrupt. I don't know what to do. I'm unable to function, and it throws up this bomb, right? This bomb picture. So that's what would happen in DOS. Sometimes it would go more silently into the night. But it would die. It would die, and of course, or you get a black screen and blue screen of death. Right?
But once we run an encoder system, I don't have to worry about importing things on every day.
Right.
He's assuring that his Windows 7 will not break if he runs that code.
No, Windows 7 has got stricter protections. Actually, there's more stringent protections in form for some in Windows 7 than there are on Unix situations. I think Tidy over here encountered a situation where the program was crashing because of a loose pointer in Windows, but it was not crashing in Unix. So it seemed to work fine in Unix, but it was just not working. It just wasn't telling you it wasn't working, but it was hiding that. And this is why segmentation faults, ladies and gentlemen, are your friend. Because they tell you something is off, go fix it, rather than just letting you blithely think nothing is wrong and you're just, destroying data in your machine. So these things can happen. Pointers, though, look, if you're careful with pointers, if you're not doing funny business, like this whole thing about casting it to a character point, that's just, you're just asking for trouble. You're leaving the gates wide open for trouble. You can treat pointers if you treat them with respect, if you treat them carefully, and you are meticulous about making sure that you allocate and deallocate things appropriately, that you handle out of memory errors, that you are insistent about deallocating something before you let all references to it go away or pointers to it go away. You can do. You can build a system that's very solid. I built many of such systems in my youth, and I know you may think that's why I look so weird now. But the point is, you can build solid systems out of it. It's just that the level of worry and the level of care that's needed, the meticulousness is compared to building a similar program in raw C, if there's a lot of memory being allocated and so on. You have to know certain conventions. You learn to enforce in C certain ways of doing things. So we have a very structured way of where you allocate, where you deallocate memory. You do clean up in very well-defined places with data structures. You can do it. And there's nothing inherently arcane or inherently bad in pointers. It's just you can get into trouble with them awfully easily if you try to, you know, act loosey-goosey with them, like cast them to other types of pointers, or like use them outside of context where they were allocated. And one of the things, maybe in the slides I linked up, maybe I want to show some pictures of that, because I want to be sure. There are some questions which came up in one of my office hours that made me wonder, maybe worried that some people weren't solid in one or two things. Okay, so suppose we have a function name, and this function calls the square root function, and the square root function, which we may have written or someone else may have written, calls an abs function, an absolute value function. Okay? Okay, so this is the sort of code we have, and you'll notice that there's a double precision. Maybe I'll record this as a separate